Yes.
Oh, nothing. I was just acknowledging that you're here now.
No,
Taking
sorry.
you off on the attendance. That's okay. Thank you. All right. We just need one more. There we go. There's Erie. Everyone is here. Awesome. Okay. Good morning, everybody. Welcome, welcome. We have one of possibly the most exciting bit of our exponential and logs chapter, and that is a new, wonderful, magical number. Just like pi, it is not only irrational, but technically transcendental, which just means it's even more nonsensical, really. It's like this whole extra category that they created for these numbers that like we really can't make better sense of these numbers. I would just call them transcendental, right? That, like, not only are they, right, irrational means you can't write them as a ratio. So I can't write pi as just, well, it's 3 divided by 5, right? A single integer divided by integer, right? 0.5, 1/2 is still a rational number because I can write that as a ratio, right? Pi, you can't do that. It is always calculated as a ratio. It's funny enough, right? It's always the diameter divided by the radius, circumference divided by the diameter, excuse me, is how you compute that as far as a circle. But that measurement, right, that initial measurement, those both can't be integers, or they will not be integers for a real circle, for a true accurate measurement, right? You can never get perfect, you're never going to get a perfect calculation, and so it's interesting. But E is our new number for today, and E is even more interesting, right? Because it's an even weirder way that we have our approximate computation. Okay, so enough teasing. Let's get to it. Let's start looking at this stuff. All right, Algebra 2. Okay, so I decided to just add on to the notes from here, right? So we've got 10.5, the natural logarithm. Okay, first of all, natural log, abbreviated ln of x, right? It's another function. It's a logarithm function. ln stands for the natural log. Why are the letters backwards is my immediate concern. Blame the French. It's all their fault, okay? It goes in proper order if it's the log natural. Okay, if you put it in French, L comes before it, whatever. But ln of x is just log base e of x, okay? So as a function, as an operation, it behaves no different than we've seen before. All of the same properties apply, okay? It's just we've set this base number. Just like we did with the common log, we set the base of 10 and say, hey, we use this a whole bunch. We're gonna pretend if we don't write it, it's 10 because it's so common. This one we use almost as much. We use e as our base so often, we needed another abbreviated shortcut. Okay, needed might be going a bit far, but we have this ln there, right? And so if ln of a equals b, right, the exponential form, the unwritten base e raised to that exponent equals a. Right? That is the natural log in a nutshell. That's all it is. It's just another very commonly used base. But the number is e. It's another one of those numbers we represent with a letter. In this case, we're using an English letter instead of a Greek letter like pi. So at this point, you need to start drilling into your mind. E is a weirdo number just like pi, okay? So all the same things that come with pi come with e. Except where does e come from? Well, e is computed this way, right? And I have a video, and in fact, I encouraged you over the weekend as part of your notes to watch a couple videos. I have another one for you here, real short, on where do we get e? Well, This is subnotation that you will see more of in calculus. Okay? But let's focus on inside the parentheses first. I'm going to take 1 plus a fraction, okay, 1 over a number, okay, and I'm going to raise it to an exponent. So if I take 1 plus 1/2, I then square it, okay, or I could take 1 plus 1/3 and cube that, okay. Think about what happens here when I have, let's go, we can go with pink, that's fine, right? Maybe I do want smaller. Right? 1.5, if this was a half, right, times 1.5. You may have done this computation enough times that you always end up with 1.25, right? You get a little bit more. It's, sorry, 1.5 times 1.5, 1.25. Right, you get a little bit more than what you started with. 5 times 5 is 25. 2, 1 times 5, 5. Let's do it 7. Okay, plus 0, 5, 1. And you get 5, 7 plus the 5 is 12. 2.25, right? 2.25. And if you did the same thing with 1 and plus 1/3 raised to the 3rd power, well, okay, so our fraction is a little bit smaller, but we're multiplying more times, so we would expect the fraction smaller. 1.3 times 1.3 times 1.3, right? Multiply all those together. Well, it's going to be a little bit smaller than 1.5 times 1.5. But I multiply by again, and this is greater than 1, so I increase it again. So it should go up. It should be bigger. What if I go way out to, like, if n is 10, 1 plus 1/10, well, that'd be 1.1 times 1.1 times 1.1, right, 10 times. So I'm increasing it 10 times, but I'm not increasing it by very much each time. See the dilemma there? Like, you're raising it, but you're not raising it as much, and so does it really get any bigger? Do we actually beat 2.25? The question is, E is actually the limit, that's what this means, the limit of n as n approaches infinity. What if we made this n as big as possible? 1 plus 1/1,000,000th to the million power. Now that's got good enough. 1 plus 1/1,000,000,000th to the billion power. How big can we possibly make it? Well, I've got a video for you here from the Mathologer that I feel actually has done this explanation the best. So if you would please listen in.
So recently we did a video on the most mysterious and beautiful identity in mathematics. E to the pi I is equal to -1. Comes up 3 times in The Simpsons, which of course makes it even more important. Now afterwards, a few people challenged me to come up with an explanation that even Homer can understand. And
all right, so he's a big Simpsons fan, right? Very commonly, it's a popular show, and you can see there in the background this very famous Euler's formula: E, that's the number we're talking about, raised to the power of pi times I. Pi we know, right? I we know. E is the newest one for us. And somebody worked out that you take all these funky, crazy numbers, right? Pi is weird and transcendental. I is imaginary. E is another transcendental. Turns out you combine them in this way and you get back to -1, which sounds absolutely ridiculous, right? Why should these 3 funky things come back to something so simple? This whole video is going to explain that, but I'm just going to do the first couple minutes where he explains how you can take just an understanding of addition, subtraction, multiplication, and division and get an understanding, an almost intuitive sense of how we came to find the value for E.
Actually, I've been agonizing over this ever since, and today I wanted to do just that. I want to explain E to the pi I is equal to -1 to someone like Homer. Okay, someone like Homer who can only do addition, subtraction, multiplication, division. So we have to remind him or tell him two things. The first one is that I is this strange complex number, square root of minus 1. I squared is 1. Second thing is just kind of a reminder. If you've got a semicircle of radius 1, then the length of the semicircle is pi. Okay? So keep those two things in mind. You have to use them later on. So the first thing I have to explain to Homer is, what is E? E. So to do that, I give him $1. And I tell him, go to the bank. Now I've arranged with the manager here to give him 100% interest over a year. Okay? So what happens to this $1 when Homer puts it in? Well, after 1 year, he has 1 plus 1 is $2. Okay? So he's got $2. Now this is actually not the best you can do with 100% interest. You can do better if you find a better bank. And we found a better bank, the Second Bank of Springfield. The Second Bank of Springfield, they calculate and credit interest twice a year. So after 6 months, what happens? You get 50% on what you've got there, so it's 50 cents, it's got $1.5. Now, another 6 months path. Half of that is 0.75, so you have to add that to 1.5, and it gives you 2.25. That's
Okay, so little life lesson here, right? Not only does the interest rate make a difference, but how often they calculate that interest rate. Notice it was the same interest rate of 100%, which realistically, completely insane, totally unrealistic. You will not find a bank or any type of investment ever that will guarantee you a 100% return on your money. Okay, that's not possible. Okay, but theoretically, if it was possible, if there was a scenario, right, where you can get 100% interest back, if you only calculate it once at the end of the year, you simply doubled your money. But what if we doubled it, but only halfway through? Right, so you got half of that 100%, and then we give you the other half. But now, notice, right, another 6 months pass, and this new half is actually half of the 1.5. It's not half of the original dollar. This is compound interest. This second calculation of interest includes the first amount of interest was already granted. Okay? And that's the difference. And that is going to lead us to E.
5, so at the end of the year, if you calculate and credit twice. Now, at the Third Bank of Springfield, they do it 3 times. So what do you get? After 4 months, you get that. After 8 months, you get that. And at the end of the year, you've got that, even more. Okay. And it's actually quite easy to figure out the general formula for this. Well, maybe Homer can't do it, but I can do it. So it's this one here. And you can probably do it too if you're watching this video. So it's 1 plus 1 divided by n to the power of n. So if you credit n times throughout the year, that's how much money you have at the end of the year. Let's just check it for the simplest cases 2 and 2.25. So for n equal to 1, so 1 plus 1 is 2, is 2. Okay, 1 plus 1/2 is 1.5, squared is 2.2. Okay, works, okay? Works in general. Now, this is really good news, but maybe what you think now, and Homer definitely thinks this is, well, I divide more and more, and I get more and more money, so if I just divide enough, maybe I get $1 trillion at the end of the year. Sadly, that doesn't work. Okay? So for example, if you divide into 125 parts, you get that much money at the end of the year, or have that much money at the end of the year. Now, if you crank up the n, what happens is, well, that number goes up, but it goes up very slowly and actually settles down to a number. So if we push the whole thing to infinity, take the limit of this, we get this number here, $2.718. And that's the absolute maximum. That's continuously compounding interest. That's what it is. So you can't do any better than this. That's E. And that's also where E kind of comes up for the first time historically. Exactly this sort of consideration, okay? Cool. So now we've got...
All right, there you go. So it comes from compound interest as the maximum possible result. You can't do any better than this. $1 becomes $2.718. Right, so at the best, 100% interest, compounded at every fraction of a second, again and again and again. At best, you can give, 271% return. Okay? So that's where we see this number used probably the most, is dealing with things like interest, compound interest specifically. It comes up in probability quite a bit, and as a natural extension, statistics, and spreads of data. The normal distribution brings E into it. And most astoundingly, probably the most significantly for you guys, is it does really cool things in calculus. This function, I guess as a function, e to the x, okay, is really special and really cool in calculus. And I encourage you to, you can either wait for it and be surprised, or if you want to read about the exponential and the natural logarithm and spoil it for yourself, it's really rather profound. Okay. But we will deal with applications later on Friday. Right now, we're just going to go with the simple stuff. Okay, just practicing dealing with the logs, the exponential, solving equations, that sort of thing. So here's a few to get us started. Let me go back to blue here. So let's try number 38 together here. If we have 3 times e to the x plus 1 equals 5. Okay? E is just a number. Okay? X is our variable. That's what we're trying to solve for. E is just a number, as if it was pi, or if it said, 2. Okay, it's 2.718, but a little bit more than 2. How do we solve for x? Well, start by at least getting the e to the x part by itself. So subtract the 1. 3 e to the x equals 4. Divide both sides by 3. So e to the x equals 4/3. And now I'm at a conundrum. My variable is stuck in the exponent. In order to get things out of the exponent, I need to unexponentiate, which means I need a logarithm. Okay? The exponent, if I just switch this from exponential form to log form, right here, I suppose I can modify this, right? Double arrowhead, right? Because we can go back and forth between the two. So I have this right now. Instead, I want natural log of that stuff equals my exponent. So ln of 4/3 equals x, right? Because the base was e, it's a log with base e. That is the natural log. Why natural? There's a lot of natural things, again, with the statistics and populations and things. When we get to the application, you'll see why they decided this one is the one that pops up in nature, okay? E comes up everywhere. It's weird. But anyways, you might notice now that just like on Monday, the common log, the base 10, we had that log button on our calculator. That's what that's for. Guess what other button we have on our calculator? Oh, that's right, the ln button. Do I still have, yes, you do. There we go, right, not now. Right over here next to 4, you have the ln button, the natural log button, and it works exactly the same. So I need to find the natural log of 4/3, or divided by 3. I'm sorry for the cutoff there at the bottom, but you can see the important bits. Enter. There's my number, 0.287, round up, 0.288. No, rude. Okay. So x is approximately 0.288. Right? That's the best we can do, right? anything with ln involving number e, you're not going to get a nice clean integer answer out of it. In fact, almost any log after this point, you're very unlikely to get a clean integer answer out of it, right? Especially any actual real application type question. All right, questions at this point? Let's try a couple more then. Why don't you guys do number 44? Go ahead and take 2 minutes, complete number 44, and then we can check in with how you did. E to the 5x greater than or equal to 25. Okay, see what you can do with that. Okay, one thing to consider with this question is we've got an inequality, not an equality this time. So let's just check in, get an intuitive sense here, because honestly, the exponentials and the logs are probably the easiest, or at least one of the easier to deal with inequalities, unlike, say, linear and quadratics, where you always got to, especially quadratics, right? Wait, is it inside? Is it outside the curve? What? E to the x is like any exponential, goes like that. Okay, and it takes off. And multiplying this by 5 doesn't change the general shape. Which is to say, this is always increasing. If x increases, my function increases. It is strictly increasing. Right? Unless we stuck a negative in front of it, flipped it upside down. It's always increasing. So when the function is greater than 25, so let's pretend right here is 25. We can just draw a horizontal line like that. From here up, right? All of this function, this is all greater than 25. All of that counts, right? So anything from there up, which means any x value, whatever we find out this is, anything greater than that will also satisfy. So we can solve this by just solving the equation part and knowing whatever we get, we just need to be greater than or equal to that, right? So it's kind of nice that when it comes to these functions, these strictly increasing functions, that the signs for the inequalities will match up, right? The sign If our function is greater than a number, then our solution will always be greater than number. Greater than or equal to, greater than or equal to. Less than or equal to, less than or equal to. Okay? So let's see. E to the 5x equals 25. Ooh, 25 is 5 squared. Maybe that'll help me. Maybe I can use that. The fact that we've got 5 here and this is a power of 5. Maybe. Problem is the base here is still e, and my x is still in the exponent. So in order to undo this, I still need to use the natural log on 25 to get back to 5x. Now to solve for x, that means I'm going to divide. So x will be the natural log of 25 all divided by 5. Is there another way we can do that? Well, this is ln of 5 squared for 5. And remember, your exponents you can move into the front, and then you'd have a 2 times ln of 5 all divided by 5. But then you have 2 up here and 5 down there. So nothing really reduces. So even though it looks like, hey, they've got a factor in common, they don't have the factors in the right place because one is the power and one of them is the base. Those don't match up, right? If instead this was 2, 4, 8, 16, 32. If this was 32, let's just imagine a hypothetical scenario. This was 32, right? So then we would have, instead of 5 squared, we would have 2 to the 5th. Then we could put 5 times ln of 2, and then the 5s would reduce. See the difference there? You have to have a matching factor in the exponent to reduce with the factor in the exponent if you're going to hope for any matching shortcuts there. But that is not the case we have here, so let's stick with this. X equals ln of 25 all divided by 5. So please be sure if you're punching this into your calculator that you type ln is one button, it automatically opens some parentheses for you. You type 25, close your parentheses, then press divide, then 5, enter. What do we get? Answers in chat, if you please. Got one answer in. Can I get a second to verify? And 3 decimals will be sufficient. Anyone going to back Marcos up on this one? All right, Gabe's got it. 0.643. Yep. 6, 4. Marcos had a 7 after that, so I would probably round that up to a 4. 0.644. Let's try it. ln of 25 divided by 5. Calculator. I guess not. Stupid ads. All right. I'll take your word on it that that's correct. 0.644. So this is why I have you guys here, right? Your calculators don't have ads. All right. And how about, can we go the other direction? What if we had ln of 3x equals 5? Let's try that one. Ln of 3x equals 5. Okay. here now our variable is in the argument of the log. So just like and the other ones, let's swap it to exponential form, see if that reveals some things. So my base is an invisible e, because this is natural log. Log always gives the exponent, so this should go up there. E to the 5, that's a terrible 5. That's better. Equals the argument of the log, the 3x. Now to isolate the x, just divide both sides by 3, so x should be e to the 5th divided by 3. Okay, where do we have that button? Well, here, I'm gonna pause this for a moment. Shh, quiet you. There we go, okay. Got it back. Got through the ad. Well, if you look real closely, and I wish I could zoom in on here. Look real closely at your natural log button, and you'll notice in the corner it actually says e to the x there. Okay, so if we want that, we got to go second natural log button. That will type e to the x. E to the whatever power we want. And now I can type e to the 5. Okay? All right, get out of the exponent there, divide by 3. Make sure your divide by 3 is not in the exponent. I'd have to double check on older calculators. Let me see here. Your batteries are low. Okay. I will deal with that at a later date. Divide by 3. Okay, let me get it as bright as I can. So if you have an older calculator, you might see something like, can we avoid the glare there? You can better see the reflection. All right, so this one, you press E to the caret. That's that same button. Okay, right down there. I got you. E caret parenthesis 5. So you have to make sure you close that parenthesis manually, then divide by 3. And then enter, what do we get? 49.471. How about this one? 49.471. That is our answer. Okay. Please verify that you can get the same thing from your own calculator. If not, let me know. This one should be straightforward, right? It's not mode dependent. We don't have to switch from degrees to radians or anything like that. So shouldn't be an issue. If you can find the button, you can get it. Any questions then from here? All right, seeing none, then I will wrap it up there and turn it over to you guys. You have your practice worksheet uploaded. Go ahead and get started on those exercises. As I mentioned, this is just, we'll start with the basics here, some straightforward practice, and then on Friday we'll do some word problems where we get to get some application in and see it in action with compound interest and population growth and all that fun stuff. Okay?